Okay, so mathematical induction is how this course starts off in abstract algebra, you know. So I have the sequence an equals 1 plus 3 plus 5 plus da da da, you know, basically on and on, plus 2n minus 1 is what you get, the expression. And an is sum of first n positive odd integers, in a way, is way how you could, in words, say this sequence. As you can see, 1 plus 3 plus 5 and so on are just odd. And I computed the first few terms. A1 is equal to 1, A2 equals 1 plus 3 equals 4, A3 equals 1 plus 3 plus 5 equals 9. Eventually you get, 1 plus 3 plus 5 plus 7, if shown, would be 16, and 1 plus 3 plus 5 plus 7 plus 9 equals 25. And you can do that for eternity, but it eventually gets really annoying because you have to keep on adding more and more numbers onto it. And there are, can keep on going for however many terms of n you want to, and, well, there's an infinite number, if you really were being technical. Point is, if we wanted, like, a to 950, the 950th terms, then we'd have a lot of trouble calculating it that way. But there's a simplified way. We have to come up with that, though, and prove it by mathematical induction. And conjecture I give for this, which is what I assume is what this could be, is an equals n squared, and it is seen by these traits. You have 1 squared equals 1, 2 squared equals 4, which is a2, a3, which, if you have 3 squared is 9, an, so a3 equals 3 squared, a2 equals 4, 2 squared, and it works so far and so far, and 4 squared equals 16 for a4. And my proof, we have to prove two things. First you have to prove a1, and then you have to prove ak plus 1. So first, a1 is equal to 1 squared, which is equal to 1. So it's true, because as we see, a1 is equal to 1. So basically, what you get from this an, the sequence an, will match what you get from the n squared, basically. Now we do this for a of k equals k, but so basically you first have to assume ak is equal to k squared is true. So that's how it was our job, true. Then we have the prove ak plus 1. So ak plus 1 is equal to ak. If you do it, basically ak plus, in brackets, 2 times k plus 1 minus 1, because 2n minus 1. Basically this is 1 plus 3 plus 5, basically eventually plus ak. It's an ak plus 1. So basically this comes from, I want to write out a little bit more. But the point is, and then you get to ak plus 1 is equal to k squared here, plus 2k plus 2 minus 1. So ak here becomes k squared, because we're assuming that's true. We're trying to prove ak plus 1. So it's plus 2k plus 2, because 2 times k plus 1 is equal to 2k plus 2, then subtract 1. And then finally, it simplifies down to, because 2 minus 1 is 1, k squared plus 2k plus 1, and you can simplify that down so that ak plus 1 equals k plus 1 squared. And that's the same as, basically, an equals n squared, ak plus 1 equals k plus 1 squared. So, yeah, the formula is proved. A slightly different variation is just using this Lucas sequence. And I wrote, basically, Lucas sequence, you can look in the book, right here. L1 equals 1, L2 equals 3, and then Ln plus 2 equals Ln plus 1 plus Ln for n equals 1, 2. You could see this written a slightly different way, but with the subscripts, but they mean the same thing, depending on which book and which way you look. So yeah, I wrote out all the terms of the sequence up to like 10, and I make a conjecture, because we want to know about odd and even. When is it odd and when is it even? Because it appears changed depending on which term. So my conjecture, you could ignore this bias I do, since the question out of where this question comes from, it asks for Lm when the sequence is defined for Ln technically, and in the same palm. I know it's kind of dumb, but I decided to do that. But let's just say Lm equals L3n is even, and Lm equals L, basically 3n minus 2 and 3n minus 1 will be odd. Let's just treat this like it's just n. Ignore the lm part, you could equal to it. Just treat this like L3n, L3n minus 2, and L3n minus 1. The point is that L3n will be even, while the other types of terms, when you're in multiples of 3, which is 3n minus 2 and 3n minus 1, those types are odd. For all n greater than or equal to 1. And my proof begins with P1 is true. So n equals 1, we have L of 3 times 1 minus 2 equals L1 equals 1. Because we know from these terms up here, 1, 3, and 4, those two terms, what we're given. So you have L2 and L3 given from the same thing. It's 3 minus 1, 3 times 1 minus 1, and this is just 3 times 1, which is equal to 4. So odd, odd, even, I said that. These would be odd, and that would be even, 3. So, it's proven. And now it's time for the second part. To actually complete this proof, we have to do, assuming P of k, basically it's P of k implies P of k plus 1 is true. So P of k is true, that's 3k minus 2 and 3k minus 1 are odd, 3k is even, and we have to show that this is true, k plus 1. And I wrote it down, basically you go through it real quick. 3 times k plus 1 minus 2 you have to distribute in, so it becomes 3k plus 3 minus 2, which becomes 3k plus 1, odd, so on. You just keep that up. And basically odd, odd, and even, we have to prove this. And we do that right here. So L is 3k plus 1 is equal to, using this Lucas sequence definition, of ln plus 2 equals ln plus 1 plus ln. We know 3k and 3k minus 1 from here, right here. 3k, 3k minus 1, 3k minus 2 we know. So 3k is even, 3k minus 1 is odd, and in general, an even plus odd number equals odd. An odd plus odd number equals even, and even plus even equals even. Okay? So that's what we do. 3k plus 1 and 3k. That's what L3k plus 2 is. It is 3k minus 1. And then we know 3k plus 1 is odd from here, as well as 3k is even. So odd plus even equals odd. So that's 2 of them proved. And the last one is 3k plus 2 and 3k plus 1, which, as shown here, are both odd. So odd plus odd equals even. That gives you. So P of k plus 1 is true. Hence, P of n is true for all n greater than or equal to 1. And you could just keep this as just all n terms and k's, but Lm is even for m equals 3n, because of how I set it up, and odd for m equals 3n minus 2 and m equals 3n minus 1. But that's because of my setup. But basically, that's how mathematical induction can work for 2 different types of problems. In general, you're just trying to keep it simple. Usually, you're not trying to overcomplicate the situation. It's usually used to prove somewhat simple formulas like this. True for something that does not appear as easy. Figure out like infinite amounts of terms, whatever term you want. It's just one way of evaluating things.